Hello everyone. I hope you are all staying safe and healthy. This is our fifth video for chapter 12, partial differentiation. And today we are going to talk about the chain rule. You remember the chain rule from MATH119. If we have functions f and g from R to R, single variable functions, we can consider composite function f of g of x, and derivative of f of g of x is derivative of f at g of x times derivative of g at x. This is known as chain rule. Today we are going to talk about chain rule for multivariable functions. But let us first consider a version of the chain rule. If z is a function of x and y with continuous first partial derivatives, and if x and y are differentiable functions of t, then derivative of z with respect to t is del z over del x, partial derivative of z with respect to x, times dx over dt, derivative of x with respect to t, plus del z over del y, partial derivative of z with respect to y, times dy over dt, derivative of y with respect to c. Okay, here you see we have a function z depending x and y are functions of t. They depend on t. So actually z is a function depending on t. We have actually a single variable, but z is given in terms of x and y, and you know x and y are functions of t. So you can consider derivative of z with respect to t in terms of partial derivatives with respect to x and y, blah blah. Now let us prove this. Suppose g of t, or c is g of t, f of x of t, y of t. We want to find an equality for derivative of g with respect to t, g prime of t. We know limit definition of derivative. It means as h goes to 0, g of t plus h, g of t plus h minus g of t over h. Okay, so here if I write everything in terms of x, we have f of x of t plus h, y of t plus h minus f of x of t, y of t over h. Okay, and I want to show that this limit will give us partial derivative of z with respect to x times dx over dt plus del z over del y times dy over dt. How can we show it? We need some modifications. We can write f of x of t plus h, y of t plus h, minus f of x of t, y of t plus h. We don't have such an expression. I'm not changing anything, so I will add it back. F of x of t, y of t plus h, minus f of x of t, y of t over h. Here, as h goes to 0, I can write it as f of x of t plus h, y of t plus h, minus f of x of t, y of t plus h, over x of t plus h minus x of t times x of t plus h minus x of t over h times f of x of t, y of t plus h. After writing, I will explain what I did one more time. F of x of t, y of t over, here I need one more parenthesis, over y of t plus h minus y of t times y of t plus h minus y of t over h. Okay, so here I just divide and multiply by x of t plus h minus x of t. For the second part, I did this with y of t plus h minus y of t. If you look at this expression, here we have f of x plus t plus h, y of t plus h minus f of x of t, y of t plus h over blah blah. You see, y coordinate is constant and x coordinate is x of t plus h, x of t, and in the denominator we have the difference of t. As h goes to 0, x of t plus h minus x of t goes to 0, since x is a continuous function, it's differentiable, so continuous blah blah. This expression corresponds to derivative of f with partial derivative of f with respect to x at x of t. And limit as h goes to 0, x of t plus h minus x of t over h is the derivative of x with respect to t. Here you have x prime of t. Similarly, here we have partial derivative of f with respect to y at x of t, y of t. And here we have derivative of y with respect to t, y prime of t. So we got del z over del x times dx over dt plus del z over del y times dy over dt. This is the end of the proof. Okay? So, now we are ready to write theorem, which is chain rule for multivariable functions. Chain rule for multivariable functions. Let z be f of xy, where x is a function of s and t, and y is, say, v of s t. Suppose u of ab, the value of u at ab is p, and value of v at ab is q. Suppose the first partial derivatives of u of st and v of st exist at AB, and another assumption, f is differentiable at the point PQ. Then theorem says that z, which is f of xy, x and y can be written in terms of u, f of u of st, v of st, has first partial derivatives with respect to s and t at AB, and they can be found by using following equalities. Del z over del s is del z over del u times del u over del s plus del z over del v times del v over del s. Similarly, del z over del t is del z over del u times del u over del t plus del z over del v times del v over del t. Okay, this is known as chain rule for multivariable functions. You have a function z depending on x and y. X and y are functions depending on s and t. So you see z depends on s and t. You can consider partial derivative of z with respect to s and with respect to t if the following conditions 1, 2, 3 are satisfied, and partial derivative of z with respect to s can be computed by taking partial derivative of z with respect to x times partial derivative of x with respect to s plus partial derivative of z with respect to y times partial derivative of y with respect to s. Here x is u, y is v. Okay, so I will skip the proof of this theorem. It can be found in our textbook. We will continue with examples. Let C be sine, okay, maybe it's better to write white. C is sine x squared y. X is s times t squared. Y is s squared plus 1 over t, and you are asked to find partial derivatives of z with respect to s and t. Okay, you see, we have a function z sine x squared times y. It's a differentiable function everywhere. First, partial derivatives are continuous, you can check. So it's differentiable everywhere. And x and y are differentiable functions. As also first partial derivatives exist, of course. And we are asked to find del z over del s, del z over del t. You see, z is a function depending on x and y are functions of s and t. We are asked to find derivative of z with respect to s. To find derivative of z with respect to x, you first take derivative of z with respect to x times derivative of x, partial derivative of x with respect to s, del z over del x times del x over del s. This is not the only branch from z to s. We have another one. Plus del z over del y times del y over del s. Okay, let us compute this. Derivative of z with respect to x is, we have sine x squared y. Derivative of sine x squared y with respect to x is 2xy times cosine x squared y. Here we are using chain rule for a single variable function. Y behaves like a constant. We are taking derivative with respect to x times derivative of x with respect to s, s times t squared. Derivative of this with respect to s is t squared plus derivative of z with respect to y. Okay, it is x squared times sine x squared y times derivative of y with respect to s, which is 2 times s. So here we are finding derivative of z with respect to x, so it's good to write everything in terms of s and t. In the last bottom we have s and t's. So it will be 2 times st squared times s squared plus 1 over t times cosine x squared, which is s squared times t to the 4th times s squared plus 1 over t plus x squared, which is s times t square times, oh, here I made a mistake, I guess. We should take derivative of sine x square y with respect to y. It would be x square times cosine x square y, cosine s square t to the 4 times s square plus 1 over t in parentheses times 2s. Of course, you can write it in a simpler form. Okay, I can leave del z over del t as an exercise. Or let me write the formula, chain rule for it, del z over del t. To find del z over del t, you should consider partial derivative of z with respect to x, then times partial derivative of x with respect to t plus partial derivative of z with respect to y times partial derivative of y with respect to c. Here we'll have del z over del x times del x over del t plus del z over del y times del y over del t. It's an exercise for you. Okay, another example. Find del over del x of f of x square y x plus 2y in terms of partial derivatives of f with respect to x and y, assuming that these partial derivatives are continuous. Or let me write clearly, f sub x and f sub y are continuous. Okay, so here we have a function f. Let me call coordinates x square y x 2y, u and v. You see, we have f of uv. We are asked to find partial derivative of f of uv with respect to x, where u and v are functions of x and y. So we have f of x square y, or just write f, it's not necessary, depending on u and v, and u and v are functions depending on x and y. Okay, we are asked to find derivative of f with respect to x. Okay, here you see we got a 3. F is a function depending on u and v. U, v depend on x and y. So follow the branch from f to x. Derivative of f with respect to x is derivative of f, partial derivative of f with respect to u times partial derivative of u with respect to x plus derivative of f with respect to v times partial derivative of v with respect to x. When we said partial derivative of f with respect to u, we mean partial derivative of f with respect to first coordinate. So remember notations for partial derivatives. Sometimes we put f sub x, sometimes we put f sub 1. Both works, but for such examples, you see, using 1 is more convenient. I mean, using x sometimes may be confusing. We mean by x first component, first coordinate. Okay? So it's better to use 1, I think. del u over, if you put x, it's not wrong, but I think it's more clear. Derivative of u with respect to x is 2xy plus derivative of f with respect to v, which is second component, times derivative of v with respect to x, which is 1. Okay? Another example. If w is f of x, y, z, where x is a function of y and z, g of y, z, and y is a function of z, say h of z, state appropriate. Right. All right. Another example. Find del z over del x if z is arctangent u over v, where u is 2x plus y and v is 3x minus y. Okay, we have a function z depending on u and v, and u and v are functions of x and y. We are asked to find derivative of z, partial derivative of z with respect to x. So to find del z over del x, consider partial derivative of z with respect to u, multiply it with del u over del x plus del z over del v times del v over del x. And derivative of arctangent function with respect to arctangent u of v with respect to u is derivative of arctangent function at u over v, 1 over 1 plus u over v square times derivative of u over v with respect to u, which is 1 over v, times derivative of u with respect to x, which is 2x, derivative of 2x plus y with respect to x is 2, plus del z over del v, which is 1 over 1 plus u over v square times derivative of u over v with respect to v, which is minus u over v square times del v over del x, which is 3. So if you write everything in terms of x and y, okay, I don't want to do all computations again. I did it before. If I did it correctly, at the end you will get minus 5y, 9x squared minus 6xy plus y squared plus 4x squared plus 4xy minus, plus y squared. Okay, of course, this is not the simplest form. Minus 5y over Here we have 13x squared minus 2xy plus 2y squared. Okay? All right. One more example. Find second order partial derivative of f of x squared minus y squared xy in terms of partial derivatives of f and here we have the assumption that all partial derivatives are continuous everywhere, assuming this is necessary to use chain rule. All partial derivatives continuous everywhere. Okay, we have f. Let me call x squared minus y squared u, xy v. So we have f depending on u and v, and u and v are functions of x and y. We want to get second order partial derivative of f. We first take the derivative of f with respect to y, then we'll get a function and we will take the partial derivative of this new function with respect to x. Let us do this together. Del f over del y, derivative of f with respect to u, partial derivative of f with respect to first component. So instead, maybe it's better to write f sub 1 uv times derivative of u with respect to x. The u is x squared minus y squared. Derivative with respect to x is 2x plus derivative of f with respect to v, derivative with respect to second component, times derivative of v with respect to x, which is y. Okay, here, I'm sorry, I made a mistake. This is del f over del y. Now we can take derivative of del f over del y with respect to x. We have f1 uv2x. f1 and f2 are functions depending on u and v, u and v depend on x and y. So to find derivative of del f del y with respect to x, we need to take the derivative of f1 with respect to x. Okay. Derivative of f1 with respect to first component times derivative of u with respect to x, which is 2x, plus derivative of f1 with respect to second component times derivative of v with respect to x, which is y, times 2x, here we have 2x, plus f1 uv, here I'm applying product rule, times derivative of 2x, which is 2. Okay, so we got the derivative of the first summation with respect to x plus derivative of f2 with respect to x will be f21 uv times derivative of u with respect to x, which is 2x, plus derivative of f2 with respect to v times derivative of v with respect to x, which is y, times y, plus derivative of y with respect to x times f2 uv, which is 0. So we get f11 x squared minus y squared xy times 4x squared plus f12 x squared minus y squared xy times 2xy. Okay, here we have also f21 x squared y squared 2x times y. Since mixed partial derivatives are equal, here you can just write 4xy, 2xy, f21 plus f1 x squared minus y squared xy times 2 plus f22 x squared minus y squared xy times y squared. Okay, if I didn't make a mistake, at the end we got such an expression. Second order partial derivative of f in terms of partial derivatives of f. Okay. I think we did enough examples for chain rule. You'll see more examples in recitation video. It's a good point to stop. My 1-year-old baby is also crying. So in our next video, we will continue with gradients and directional derivatives. Thank you. Have a nice day.